Okay, so today we're going to talk about artificial neural networks. This is a very broad topic that nowadays is known under the notion of deep learning. So neural networks have been there for many decades now. So it's the concept itself is not anything new. What is new is to focus on more sophisticated structures in a sense that you can deal with more complicated problems. Um, we're not going to be specifically discussing the deep learning type structures and algorithms. Instead, I'll discuss at a high level what neural networks are, and then we'll give you some pointers along the way. So if you were more interested, you can kind of look into more deep learning solutions. Before we start our conversation on neural networks, the one point that I wanted to make, and I want all of you to remember this, is that artificial neural networks, despite the fact that they are powerful techniques for classification, for control, for identification, for function approximation, for all these different types of applications, I wouldn't recommend them to be your starting points. So every time you want to apply a data analytics model to a problem, I would highly recommend that you start with some of the most um, mathematical techniques that we talked about for regression classification clustering. And if you feel like the problem is too complicated and the model you have been working on is not providing a good performance, then I think it would be the right time to move to neural networks. The reason is that neural networks, despite their powerful performance, they lack interpretability to a large extent. So this is one of the important things when we talk about any type of data analytics model. And you have seen this in the examples we've discussed in this course, where we look at a model, we look at the structure, we look at the coefficients, and we're able to make some deductions, some conclusions about what they represent. And for example, if I change this parameter or that variable or this input, what kind of improvement or degradation I would expect to see in the behavior of my model. Neural networks lack that capability. So oftentimes, in contrast to mathematical techniques, which are more like a white box approach, we often refer to black box or gray box approaches when it comes to neural networks, because it basically means that you're providing the input and then it's spitting out an output. How this input and output set are related to one another, you don't really know. It's not easy to interpret that. So don't use them as your first go-to approach. Go through the exhaustive list of the things that we have discussed in regression classification clustering. Try those models out, and if they don't work, then start with neural networks. All right, so let's start with the basics. What neural networks do is they try to mimic the nervous system in the human body. They try to create mathematical representations for neurons. Neuron is a Greek word for nerve cell, and in human body, it's basically a very, very complicated process that does electrical signal processing as well as processing of biochemical stimulus. What happens in an actual neuron is that you will receive your inputs, or basically you get excited through the dendrites, and then while these inputs are received by the neuron, they are being processed in the brain, and then it generates an output. This output is going to be sent through the axon and delivered through these terminal buttons to the next neuron. So these different neurons are typically interconnected. One excites the other one, and the other one excites the one next to it. And this process continues until your body does whatever it intends to do. The numbers associated with these neurons is really staggering. We have about 100 billion neurons in our brain, and they conduct about 100 operations per second. So if you add it up in human brain, you have 10,000 billion operations per second. So this is a very amazing feat. And our attempts to model this through artificial neural networks really is a very, very high level approach. We are nowhere near the true sophisticated mathematical model of these neurons. What we try to do is we try to mathematically model a neuron, and we call it a perceptron. So again, looking at what a neuron looks like, you have your dendrites, which would be the receiving end for your neuron, and then you have the nucleus, which is like the brain of the neuron, receives this information, processes it, and then generates an output. Then this output will be transmitted to the next neuron through the terminal buttons. And what terminal buttons do is they send neurotransmitters, which are going to be absorbed by the next neuron. We try to model this mathematically. So our model is very, very simplistic, but kind of does the job. So the idea is this. If you have your inputs, x1 and x2 and x3, so these are the inputs to the dendrites, depending on the length of the dendrite and the strength of the dendrite, some might actually amplify the input, some might attenuate it. We typically model this using a set of weight parameters. So every input that is received by the neuron is going to be weighed according to those WI parameters. The weighted inputs are then added together using the summing junction, and that's pretty much it for us. So we don't really have a function that represents how the nucleus processes this information. The only thing we do is we add what we call an activation function. This activation function is kind of supposed to represent what a nucleus does at a very, very high level. So it doesn't have any type of specific functionalities. The only thing that it does is it ensures that the output that is generated by that neuron is going to be bounded so that the system, the mathematical system that is, does not become unstable. So these inputs, to recap, these are the inputs that are triggering the neuron through the dendrites, the WIs representing the strength of each dendrite link, and then all the weighted inputs are added together and then fed through an activation function. In the most straightforward way, this activation function is basically a hard limiter, meaning that it says if my argument, u, if it's positive, I'm going to spit out a 1, and if it's negative, I'm going to spit out a 0. This was the original mathematical perceptron model that we have, which is basically like the father of all the neural networks that we see today. Today we have expanded that model. So we have other choices for activation functions. In addition to that hard limiter, which was the basic, the most, the simplest model we had. Now we have a model which is a ramp, we have a sigmoid function model, and we have a hyperbolic tangent model. Sigmoid and hyperbolic tangent model are more desired and are used a lot more often because they're mathematically more well behaved. Typically, what you expect from this activation function is you want it to be monotonic, you want it to be bounded, because again, remember, one of the main objectives is to limit the output of the neurons so that the outputs don't go all over the spectrum. And also, in order for this to be mathematically well behaved, you want the function to be continuous and differentiable. As you can see here, the hard limiter and the ramp function are not differentiable, but sigmoid and hyperbolic tangent are. Which is why these are more commonly used nowadays in a lot of neural network architectures. So the function for the sigmoid function would be 1 over 1 plus e to the power of minus u. And again, to remind you of what that means, is this u, which is the sum of all the weighted inputs. Once it's applied to your activation function, the sigmoid will generate an output of this form, which is this green line here. Hyperbolic tangents, on the other hand, would be 1 minus e to the power of minus 2 times u divided by 1 plus e to the power of minus 2 times u. The difference between hyperbolic tangent and sigmoid is that the first one basically gives you an output that could be positive or negative, whereas sigmoid only provides a positive output. It doesn't really introduce any differences in the performance of the system, at least based on my personal experience of working with neural networks. The only difference is when you use one versus the other, the weight parameters, those W's, when you train them, might change. For example, in one case, the W parameters might be positive and negative. In another case, they may end up being only positive or only negative. That's the only difference that at least I have witnessed based on my experience. Otherwise, performance-wise, both of them behave the same way. Now, there are a variety of different types of neural networks, and as I said, some of them specifically classify under the broad category of deep learning. We're not going to be talking extensively about those. There's only one category that I will discuss that will fall under deep learning. The other ones that we'll talk about today are really the most basic structures for neural networks. Before we get to that, though, I just want to make a point that this notion of deep learning is a little bit, in my opinion, it's a bit of a buzzword. So, I mean, many of these fundamental neural network structures can actually be considered as a deep learning network, but some people have like a specific definition of what deep learning means, and there are some specific structures for neural networks that would qualify as deep learning networks. In any case, one of the most common types of neural networks is the MLP. MLP stands for multilayer perceptron. This network consists of 3 layers of neurons. One would be the input layer, one would be the hidden layer, one would be the output layer. Typically, the input layer neurons don't really do anything. They just receive an input and then they distribute it to the other neurons. So they are neuron by name only, but by functionality, they don't do anything specific. The main neurons that have activation functions of their own would be the neurons in the hidden layer. So these guys. These neurons have an activation function of phi. They receive a summation of inputs from the input layer. They process it and generate an output and send this output to the neurons in the output layer. The neurons in the output layer have an activation function which is linear. And essentially what that means is they receive all the inputs and then they sum them together and then generate an output. So basically the moral of the story is that the neurons in the input layer and in the output layer don't have any specific job to do it. They just, receive the inputs, add them together, and then generate a signal. The neurons that do majority of the job would be the ones in the hidden layer. Now, back to that notion of deep learning versus shallow learning. Again, there is a school of thought among data scientists that they believe the MLP with one hidden layer, that would be shallow learning neural network. And if you add multiple hidden layers, then that would be a deep learning network. And again, this is not like a mathematical definition, but just so you're aware of some of these distinctions. In majority of engineering application, however, it has been shown that an MLP network with one layer of hidden neurons, that would be sufficient, and you typically don't need to have additional layers. The one exception would be applications such as, for example, face recognition or speech recognition. These are the applications that it has been not mathematically proven, but it has been shown that by adding multiple hidden layers, you are likely to get a better performance. Anyway, let's see how this neural network operates. So basically what happens is you have your inputs, which are applied to the neural network. Now, every neuron in the input layer has its own input and then applies the input to every single neuron in the hidden layer. These inputs, however, are going to be weighed based on the weight parameter. So as you can see, for example, the input to the neuron J, so let's say this is neuron J, in the hidden layer would be the summation of all the xi's, so all the x1, x2, xm, all the xi's multiplied by the corresponding weight variables. So that means between, for example, input 1 and neuron J in the hidden layer, that X1 is going to be multiplied by WJ1, which is WJ1, meaning that the weight parameter associated with this particular link. And then, for example, X2, let me use a different color, X2 will be applied to neuron J by being weighed with a function of J2. And then, for example, X3 would be the same way. So this would be applied with a weight of WJ3. So this is how all these input signals will be weighed and then summed together, and this would be the activation signal. We call it activation signal because that is the signal that will be exciting the neuron in the hidden layer. Now this neuron receives A of J, the activation signal, and will generate an output signal, which we call decision signal. So A of J will be somewhere here, and D of J will be here, the output of the neuron in the hidden layer. How this output relates to the input or the activation signal of the neuron, that depends on the activation function. This phi that I'm showing here could be, for instance, a sigmoid function, a hyperbolic tangent function, two different types of functions. So depending on what that activation function is and what the activation signal is that the neuron receives, it will generate an output, which in this particular lingo for MLP, we call it the decision signal. Now the DJ...
Excuse me. Do the inputs have any bias or constant, like BI?
They could, yes. They could have a bias, which is typically a constant of 1.
Okay.
Now, these decision signals, DJs, will now be added together and then weighed based on, again, a different set of weight parameters to generate your output. So let's consider, for example, this output here, let's call it y hat of k. This y hat of k will receive the inputs from the first neuron in the hidden layer, the second one, the third one, all the way to neuron number n in the hidden layer. Now this would be all the outputs of the neurons, but those outputs are going to be weighed based on the weight parameters. So this is going to be, for example, V of K1, this is V of K2, V of K3, and so on. So again, y hat of k, so that means the kth output of the neural network will be the summation of all the outputs that are coming from the neurons in the hidden layer, weighed based on the weight parameters. What you notice here is in this neuron, in this neural network, I have two sets of weights. One would be the input weight parameters W's, which will be multiplied by the input signals and then applied to individual neurons in the hidden layer. And then I also have the output weight parameters. These are the weight parameters that are multiplied by the outputs of the neurons before they are applied to the output of the neural network. When you train a neural network, your job is basically to find what these W's and V's are. Once you know the W's and V's, essentially you know the structure of the neural network. All right, so how do we do this? This is a little bit mathematical, and next week when we do the neural network workshop, I will actually walk you through the procedure here, how you should basically code this in MATLAB or in R or in Python. But today we're just going to look at it from a mathematical perspective. So essentially what we try to do is we try to find the set of weight variables, W's and V's, in such a way that the some error function that I define would be minimized. Now this error function, for example, going back to the structure that I have here, the error function could be based on the difference between the actual outputs and the estimated output. So for example, I know that the neural network has to estimate y of k, which is my actual output. Let's say This network has just one output, and this output is, let's say, the temperature for the next hour. Imagine this neural network is used for predicting the temperature based on the current temperature and the wind speed and humidity and things like that. So this is the actual output that I'm hoping the network will predict for me. But in reality, of course, the network will predict its own output, which typically I show with putting a hat sign on top of it. So when I have a hat sign on, that means this is the estimated value. So this would be the actual value. This would be the estimated value, right? And then you can define an error, which would be, hey, what is the difference between the actual value and the estimated value? This could be one metric, for example, for the error. So what we do is we try to find those weight parameters in such a way that this error function that I define is minimized. That would be the optimum set of weights. In order to do that, for MLP networks, we use a method called steepest descent. That means we make adjustments to the weight parameters. We update them at every step, at every iteration, in the direction of the steepest descent, meaning that my weight parameters at the next time step will be the weight parameters at time t minus eta, which is some learning parameter, or learning rate parameter, typically a small gain in the form of like in the range of maybe 0.05 to 0.1 times the gradient of that error function. And the argument is that if you update your weight parameters this way, then your error value will actually start improving at every time step. Mathematically, this is easy to see. Imagine you want to find the Taylor expansion of the error function. So you will say error at time t plus 1 would be the error at time t plus the gradient of the error times delta w, the changes in the weight parameters, because remember that error is a function of w. If I now replace delta w from here, so delta w would be w of t plus 1 minus w of t, which from here, that would be negative eta gradient of e. If I replace it here, this is what I will get. So that means that my error at the next time step will be the error at the current time step minus eta, which is a positive value, times the gradient squared, which is a positive value. That means that the error is bound to improve at every step. I have to make a note here to clarify what I mean by T. In neural networks, you could have different indices. You can train the network based on samples you receive in time, or you can just simply train them based on samples. If you're training them in time, meaning that this is an online training scheme, you receive one set of inputs, you apply those to the network generates an output, you compare this output with what it should be, form an error and update the weights, and then wait for the next time step to receive another input. This would be training through time, so the weight parameters would be a function of time, as I'm showing here. So that would be the weight parameters at time t based on the input I received at time t, or the weight parameters at time t plus 1, for example, the next time step. Sometimes the notion of time doesn't make sense, however. For example, it might be one neural network that you're training based on 1,000 samples. So you will apply one sample at a time, you see how the network operates, you train or update the weight parameters, and then you apply the next sample. In situations like that, typically what people do, instead of using the index of time, they say index for sample s plus 1 would be the weights for sample s minus what we have here. From your perspective, from an implementation perspective, this really doesn't make any difference. I mean, whether you define it based on an index of time or an index of sample, both of them would be the same thing. What I'd like you to remember here is that, again, our objective in training a neural network is to update the weight parameters in such a way that the error function that I define will be minimized. Now let's see what that means. In order to implement that steepest descent method, we will have to define some sort of an error. The best type of error that I can define would be the difference between the actual minus estimated. Again, remember, when I have a hat sign here, that means this is the estimated output provided by the neural network. So I will define my instantaneous error as actual output y of t minus the estimated output by the neural network y hat of t. And again, I emphasize, if this is not training through time, you can just say error for sample S would be the output for sample S minus the estimated output for sample S. Then what we do is we define that error function to be 1/2 of norm of E of t squared. Now, if your neural network has just one output, let's say, again, that example I gave you previously, for instance, estimate the temperature, the outdoor temperature. It's just the outdoor temperature, that's your only output, so your error is going to be actual temperature minus estimated temperature. However, imagine that your neural network might have multiple outputs. For example, you have a neural network to predict both temperature and wind speed and solar irradiance in the next hour, for instance. So that would be 3 outputs. In this case, your error would be a vector of 3 by 1 consisting of outdoor temperature minus estimated temperature, outdoor wind speed minus estimated wind speed, and what was the other one? I guess I said humidity. So I'm sorry, maybe I said solar irradiance. So solar irradiance minus the estimated solar irradiance. So your error is going to be a vector. Because of that, you will have to use the norm squared. Now, the gradient of E is going to be derivative of E with respect to the W's, the weight parameters. And in this case, that would be E of t times the partial derivative of E with respect to W. So plugging this into the equation that we had for steepest descent, that means that the weight parameters will be updated according to this equation. The weight parameters for the next step or for the next sample, whichever you choose as your index, will be the current weight values minus my learning rate parameter, again, between 0.05 and 0.1 typically, times the error, times a derivative of error with respect to W. If this is again, a single output neuron, this is going to be a 1/1 value. If it's a multi-output neuron, this is going to be a vector, which will then multiply by a matrix. So the dimensions would always be right. The dimension of this portion would be of the same dimension of the W's, which are your weight parameters. Let's look at it in a little bit more detail. This algorithm that I showed you is basically based on the foundation of steepest descent and least mean squares. However, there have been different methods for implementing this, different numerical methods, I should say, for implementing this for neural networks. The most well-known method is known as backpropagation algorithm. This backpropagation algorithm was invented in the 70s, and the idea was as follows. You have a neural network, you apply a set of inputs to it, the network will operate through its own weight parameters, the activation function, the output weight parameters, and will generate an output. This is your estimated output. You compare this estimated output with the actual output, and that will give you an error. And then what you do is you backpropagate this error through the network from output to the input. And when you do that, this backpropagation will give you update equations for these V parameters and these W parameters. So that was the whole idea behind backpropagation. Mathematically, you can show it like this. Consider I'm looking at the output weight parameters, W's, right? So based on the equation that I had before, again, the steepest descent method, my V, let's say V of Kj, that would be the weight parameter that connects neuron J in the hidden layer to, let's say, neuron K in the output layer. So that particular parameter is VKJ. VKJ for the next time step or for the next sample will be the value that I have now updated this much minus eta times the error, notice, for that particular neuron times derivative of error of that neuron with respect to that particular weight. And again, if you notice, this is not different from what I showed you here, except that here I'm just giving you like a generic W as a weight, whereas in this set of equations, I'm looking at one particular weight. I will show you later on, this is going to be next week for us, that there is an easy way to basically code this in MATLAB through a loop so that it does this for every individual weight parameter that you have. So let's work with this a little bit. So VKJ at t plus 1 is VKJ at t minus eta times error. And then I can take this guy and break it using the chain rule of partial fractions, partial derivatives, sorry. So what happens is instead of saying derivative of EK with respect to VKJ, I will say derivative of EK with respect to YK hat times derivative of YK hat with respect to VKJ. And again, you remember the chain rule for partial derivative, so I can basically choose any variable in between, but typically what I want to do is I want to choose a variable that makes sense. Okay. Now let's look at this. EK, derivative of EK with respect to YK. Let's see what EK was. EK was YK minus YK hat. So naturally, derivative of EK with respect to YK hat is just going to be minus 1. That minus 1 cancels this minus 1 and becomes a positive sign. How about YK hat? So YK hat is going to be summation of all the DJs times all the VKJs. Basically, that means all the decision signals of the neurons in the hidden layer will be weighed based on the corresponding weight parameter that is related to the link that connects them to neuron K. Added together, that will be your YK hat. So if you want to find YK hat with respect to the derivative of YK hat, that is, with respect to one particular weight, it would be this signal multiplied by it. Why? Because again, let me clarify this. Let me expand this here. So that means YK hat is going to be, let's say, D1, VK1 plus D2, VK2 plus DJ, VKJ plus DN, VKN. So if I want to find the derivative of this guy with respect to one particular VKJ weight parameter, derivative of this with respect to this, or partial derivative that is, would be D of J. So all you have to do is, in order to update the weight parameters, is you will consider what you had before, and then you update it by your learning rate parameter times the error of that particular neuron times the decision signal of the neuron in the hidden layer that was providing input to that neuron. This will tell you what the new weight parameter will be for that particular link. And of course, you do realize you have to repeat this for all the weight parameters in this section of the network. So for between every one of those neurons in the hidden layer and every one of the neurons in the output layer, this is the equation that you basically have to write in the form of a loop to keep updating those weight parameters. This was the easy part. So output weights are relatively easy. When it comes to input weights, things become a little bit more complicated because we have to expand the partial derivatives using the chain rule. So again, I would do the same thing. I would say now, let's say I'm considering the input weight parameters. I would say for a particular link, let me use a different color here. A particular link, let's say between neuron or input I and neuron J. So this W here, I'm going to show it here. This W will be WJI, goes from I to J. So the WJI at the next time step will be whatever I have now minus eta times derivative, partial derivative of E with respect to W. Now using the chain rule, I break it down into multiple portions. I would say the partial derivative of E with respect to DJ times partial derivative of DJ with respect to AJ times partial derivative of AJ with respect to WJI. Again, chain rule can be applied in any way we want it to. So we don't really have any limitations in that sense. In terms of the first portion, so for the first portion, we have partial derivative of E with respect to DJ. Remember that E itself, if I have K outputs, the capital E would be 1/2 of summation of all the EKs squared. Essentially, this is nothing but this guy. So this was my definition for E, which I'm basically showing here as a summation. So I want to find the derivative of this with respect to DJ. I can take the summation out of the partial derivative. So that would be 1/2 of summation of then partial derivative of EK squared divided by, with respect to DJ. And then this would be partial derivative of EK times partial derivative of EK with respect to DJ. And this one, again, I can break it down a little bit further using the chain rule. Instead of EK to DJ, I can say EK to YK hat times YK hat to DJ. And exactly like I showed you on the previous slide, this would be EK times VJ, because this one is basically -1. So now I have that negative sign here. I had EK, so that remains as EK. Derivative of YK hat with respect to DJ is VKJ. This takes care of this term here. The other term would be this guy, AJ with respect to WJI. So let's remind ourselves what AJ was. AJ was the activation signal of a neuron. So this AJ was basically X1, WJ1, X2, WJ2, XJ, WJ, or let's say, what am I using here? JI. So let's say XI, WJI, XN, WJN. So if I'm looking into the partial derivative of AJ with respect to W, let's say some WJI, the partial derivative of this with respect to this is just going to be XI. So that is the XI. So my equation will now be WJI at the next time step will be WJI at the current time step plus that eta, learning rate parameter, plus this term times this guy times this guy. This is what we didn't talk about. Derivative of decision signal with respect to activation signal. So what is that exactly? Well, if you look at a neuron in the hidden layer, it will have an activation signal and it will generate a decision signal. The decision signal is derived based on the type of activation function that I have. So derivative of DJ with respect to aj will depend on what this function is. If that function is a sigmoid function, this partial derivative is going to be dj times 1 minus dj. And if it's the hyperbolic tangent, it's going to be 1 plus dj times 1 minus dj. So by plugging in these values, what you do is you can basically update your weight parameters. Don't worry about it if it sounds a little bit vague right now. Next week when we do the exercise on actually coding this in MATLAB, you will see how these equations need to be coded so that in an iterative process, you can basically start updating the weight parameters. And we typically update those weight parameters until the error becomes reasonably small. The examples that I have given you so far are for an MLP network that is trying to estimate something. For example, in my discussion, I said, for instance, you're trying to estimate the temperature or the humidity level or the solar radiance or wind speed, things like that. So that would be a continuous variable. In a sense, you can see that maybe the neural network in this case can be thought of as a nonlinear regression solution. However, neural networks, in addition to being used for applications like that, they can be used for classification. This is where you have different functions and different inputs, and you want to classify them as belonging to one class or the other. The same type of network can actually be modified to be applicable in a case like that. So for example, one way would be having multiple output neurons. So if you have like different classes, for instance, you can have multiple output neurons, each one providing an output which is related to their class. For example, let's say I have these different inputs, and these are the inputs in the hidden layer. And let's say I have 3 outputs. So imagine the input in this case would be the characteristics of an animal. And then what I would try to do is I would try to basically see if this animal is a lion, is a tiger, or is an elephant. So as the input, you will perhaps say, you will provide the height of the animal, the weight of the animal, and other features. And then this would be the output for lion, for tiger, and for the elephant. So you can then train your network in such a way that whenever you apply height and weight and other characteristics associated with a lion, it generates a 1 here and a 0 and a 0 here. And every time the input is associated with a tiger, you would want it to generate 0 and 1 and 0. And as you can imagine, every time it's something related to elephant, you would like it to be 0, 0, 1. So that's one way to do it. You have multiple neurons, and then they will generate or they will trigger, different neurons will trigger in the output based on what class the input belongs to. This is one way to do it. Another way to do it would be having a neuron in a series of neurons in the hidden layer, and then one neuron in the outputs. And then for this neuron, you will say, if it's a lion, generate a 1. If it's a tiger, generate a 2. If it's an elephant, generate a 3. This is another way to design your network. There's really not much of a difference. I mean, both of them should work fine. But you probably remember from our discussion in the topic of regression that having this type of output in certain situations might be problematic because the network learns that there is a difference of 1 between a lion and a tiger, and a difference of 2 between a lion and an elephant, and a difference of 1 between a tiger and an elephant, which may or may not be the case. So this is one problem with that. However, this is another easy way to train your network. All right, so that network that we talked about was MLP, and I decided to spend more time on that because this is something that we're going to work on more, and you have one homework on this later in the semester. But just to give you a feel for other types of networks that are out, neural networks that are out there, we'll just briefly discuss some other examples. One of them is the RBF network, the radial basis function network. From a distance, this looks exactly like an MLP. Again, you have your input layer, you have your hidden layer, and then you have your output layer. There is a difference, however, between RBF and MLP. Instead of having the activation functions in the form of sigmoid or hyperbolic tangent, which is the case for MLP, in RBF, the hidden layer neurons have Gaussian functions activations. What does that mean exactly? Gaussian functions, of course, this is a multi-dimensional Gaussian function, so it would have a center and it would have a standard deviation. These functions essentially try to map your input space. Let's think about a very simple case of a two-dimensional space. So you have a two-dimensional space and you're typically, your input data, let's say, are scattered along that input space. What this RBF does is it tries to first cluster this input space into multiple clusters, each one being one of those neurons. So it will essentially allocate each neuron to part of this input space. So each of these will have its own mean and its own standard deviation. Think of it as a two-variable Gaussian distribution function. So if you look at it, it would be something like this. It's in the three-dimensional domain, it would be something like this. This would be your mu j, then this would be, for example, your standard deviation, right? So what this RBF does is it asks the neurons in the hidden layer to start learning the local patterns in the input space. Each neuron will learn the local pattern, however. It doesn't learn the entire pattern in the data. So for example, your neuron number 1 in the hidden layer might have a mean and standard deviation that allows it to only learn the dynamics and patterns of this portion of the data. This might be neuron 5, this might be neuron 11, this might be neuron 21. So it doesn't really matter. I mean, there is really no rhyme or reason to where the neurons are going to fall, but essentially each one is going to learn a local pattern. And then you will have your weight parameters, which are in the output. So in the input, we have no W. All the links connecting the input to the hidden layer neurons, they will have a weight of 1 essentially. That means we have no W, but we do have our V. So what you do typically to train your RBF is using an unsupervised learning approach, which is typically clustering. You essentially you allocate neurons to different portions of the input space by determining what their centers, the mu-j's are, and what the standard deviations are. And then once you have allocated the neurons to the different portions of the input space, you use a supervised learning approach using backpropagation, for example, to update the output weight parameters. And that is done exactly the same way as we did for MLP networks. RBF networks are a lot more effective in classification problems compared to MLP, because again, as you can imagine, because of the localized behavior of the neurons, they can learn the different local patterns and behaviors better than what MLP does. MLP, on the other hand, has more of a global approach. So it looks at the entire data set as one data set. It doesn't have that local sense that RBF has. Moving on quickly to some other examples of neural network structures, functional link is another one. Functional link, what it does is it says, if you provide me with a series of inputs, before I train my network, I expand this input set into an expanded list. And then I try to apply those expanded inputs to my network. This is something that you probably have seen before and you're familiar with. You may be familiar with the Chebyshev functions, but you're certainly familiar with the Fourier series. Essentially, the idea is that if you have any type of arbitrary function, you can approximate this by a sufficiently large number of orthogonal functions. So as long as you can map them to another input space, which is orthogonal to the, in which all the dimensions are orthogonal to one another, you should be able to approximate that initial function. In Fourier series, of course, those orthogonal functions were sine and cosine. In Chebyshev, these are the different orthogonal functions that we have. In functional linked neural networks, it basically gives you the option of either using sine and cosine or Chebyshev functions or different types of functions. You can even use wavelet functions for that matter. So what you do, let's say you have three inputs, x1 and x2 and x3, then you will expand this three-dimensional space to, let's say, I have functions phi of 1, phi of 2, phi of 3. These are the orthogonal functions that I have. So x1 will be expanded in the direction of phi 1 of x1, phi 2 of x1, phi 3 of x1. Likewise, x2 will be expanded to phi 1 of x2, phi 2 of x2, phi 3 of x2. And the same thing for x3. Now, instead of having a three-dimensional input space, you have a nine-dimensional input space. So the idea behind functional linked neural networks is that by expanding the input space, you can learn the dynamics and patterns more effectively. You will expand it, and then the rest of it is just going to be exactly like an MLP. In this particular case, these newly defined 9 dimensions will now be the inputs that are provided to your MLP. You train the network, and then it generates an output. You compare it with the actual output, form an error signal, and then use that error signal to update your weight parameters. These neurons that, these neural networks that I described today, most of them, as I said, classify under the notion of shallow learning neural networks. The only exception is the network that I'm discussing now, the recurrent neural network. This is one network that people often classify under deep learning. This type of neural network is suitable for certain type of applications, in particular applications in which time dynamics are actually very prominent. In situations like that, what you do is the structure initially looks a little bit like MLP, with the difference that you have a series of inputs that you apply to the system in addition to series of states. So some of the outputs of the hidden layer neurons are fed back in the form of the inputs. Those of you who have had, I believe, 310 or 311, you probably remember this model in the form of a state space equation, in which your x dots was ax plus bu, meaning that your new states would be generated by what they were before plus the input. So this would be the input in that case, and then these are your states that you find the time lag value, and then this will be the older states that will be applied to the input of the neural network. RNNs are very difficult to train, I must say. Their training is done through a modified version of backpropagation, which is backpropagation through time. So for every training step, you have to run it multiple times. And a lot of times it's possible to run into a situation that weights become too small and the network is unable to approximate, for example, the output that you're looking to or the function that you have in mind. But if you choose the right learning rate parameters and the truncation depth, this is the number of the number of iterations that you have to have for each training cycle. If you choose those correctly, then these are powerful solutions for networks that have high fast-changing dynamics. All right, let's talk a little bit about some practical considerations when it comes to neural networks. In a lot of these statistical models that we've talked about so far, you have seen that we have closed form mathematical equations. We saw this for regression problems that we found. We saw this for some of the classification, some of the clustering approaches we discussed. So this is good because the solution is going to be parametric based on the different parameters that you have in the system. In neural networks, however, this is not the case. In the case of neural networks, you basically have to solve an optimization function. And this optimization function is highly nonlinear. And there is absolutely no guarantee that by solving it, you will find the global optimum. So essentially what I mentioned in the previous slides, you can think of it like this. You want to minimize the sum of errors over all the samples or all the time steps, whichever you choose as your index, subject to the equations of this is your error, this is the estimated value, this is a decision function, and this is the activation function. The one thing you notice here is that you have a nonlinear function here, phi, which consists of exponentials. So in the most general case, this is going to be a nonlinear and non-convex optimization problem. What is the problem with that? When you have a problem which is optimization problem which is convex, that means you have one global optimum. So if you start anywhere on this surface and apply the steepest descent approach, you will eventually get to the global optimum and you will stay there. When you have a non-convex problem, your error surface is likely to have a lot of bumps and valleys, something that I'm showing here. So one of them could be your global minimum, but you can have a bunch of others that are local minimums. When you choose the steepest descent approach, you will start moving towards one of the minimums. And then when you get here, you cannot move any further, because if you start moving, continue your movement, you will see that error becomes larger. So steepest descent will tell you that, no, you have to go back, because this is a direction that worsens the error. So you will be stuck here thinking that this is the best solution, whereas this guy is the best solution. So this is a real challenge with neural networks. So a lot of times, despite the fact that your weights converge to some values and your error surface becomes smaller and smaller and converges to some minimum value, you can never say with certainty if this minimum value is global minimum or just a local minimum somewhere. Where you end up really depends a lot on the initial values that you choose. Remember that these weight parameters, you have to initialize them randomly, right? So depending on how this randomization works, you may end up here. You may be lucky enough that you start somewhere here and then you actually do go to your global minimum, or you may, start here or here or here, in which case at best you will get to a local optimum. So that's something that you have to keep in mind, that there is typically no mathematical proof that your neural network weights have converged to the global optimum. Some other things that you have to keep in mind, just like we have talked about pretty much any other approach in data analytics, when you have input signals that, or input data points that have features with multiple different ranges, you want to make sure that you normalize all of them together so that one range doesn't overshadow or overwhelm the others. If you're looking at, let's say, your inputs being people and their attributes, one attribute being height, which would be somewhere from like 5 feet to 7 feet, another attribute being salary, which could be between $70,000 to $150,000. All of a sudden, 70,000 to 150,000, this completely overshadows your height, which would be like between 5 and 6 and 7. In a situation like that, you want to normalize everything so that all your input values are actually between -1 and +1. Another approach which is beneficial to do is to do feature reduction. Typically what you can do is if you have a high dimensionality input data set, you can apply PCA to this to remove some of the features that are not very relevant. This actually has some benefits. One is that it helps you remove irrelevant features, so it improves the effectiveness of your neural networks. And at the same time, when you have less number of features in the input. Remember that your features are going to be the number of input signals that are being applied to your neural network. So for example, this could be the person's height and weight and salary and age, for example, right? So if it just so happens that, for example, weight is irrelevant, by removing this, what I would do is essentially I would reduce the number of weights that I have to estimate. So I will have lower dimension W matrix, which is always beneficial for me. I have less parameters to estimate, and that improves the effectiveness of my model. Another thing to be aware of is a dilemma in neural networks that is known as stability adaptability dilemma. There are some systems that are fully adaptable, meaning that every time they receive a new input data point, they go through the training. Now, these have the capability of being able to respond to changes in the system. However, because the weights are undergoing changes all the time, that means they keep forgetting the previously learned information. Opposite of this would be systems that are fully stable. These are systems that they look at all the training data at once. They use the entire training data to update the weight parameters. Once they have converged to some local minimum, let's say, the weights are fixed. So as you get new data points, nothing is going to change anymore. The advantage of these systems is the fact that they maintain a memory of what they have learned before. The disadvantage, on the other hand, is the fact that they cannot adapt and adjust to new dynamics that they haven't seen before. Which one is the better approach? There is no easy answer to this. So as a data scientist, you basically have to decide on your application of interest. Is it likely to continuously go through changes, or the changes are far and few in between? If it's going through changes all the time, maybe you have to adapt the model on a regular basis so that the weights get adjusted based on the new patterns and new dynamics. However, if the patterns are pretty much remain the same and it's very rare for you to see new patterns, then in that case, you train your network once and then you fix all the weight parameters without changing anything. As a data scientist, you may need to decide on what type of neural network you have to start with. So these are some rules of thumb that you can use. If you want to approximate the behavior of a function, for example, a regression type application, MLPs and functional link networks are the best ones. If you have classification purposes, RBF would be a better option, and you can basically start with that as your initial model. And if your model has some dynamics, fast changing dynamics incorporated in it, RNN is perhaps a more appropriate model. Regardless, for different types of applications, because these, especially once you code them parametrically in MATLAB or R or Python, you should be able to just, change the number of neurons and things like that, and then run different models for the same problem. So it's typically not a difficult thing to do, to run multiple network structures for the same problem to see which one will give you the better results. And the last one is how to decide on the number of neurons. So essentially, when somebody tells you, I have a neural network, and they have to identify a few things for you to have full knowledge of what type of network it is. One would be the class of the network, whether it's MLP, RBF, RNN, things like that. The second would be the number of neurons in the hidden layer. And then the third is going to be the input and output weight parameters. All right, so these are the information points that will basically identify all the details we need to know about the neural network. The number of neurons in the hidden layer, that's a very important design parameter. And it's something that is often decided on based on trial and error. If you have too few neurons in the hidden layer, your network may not be powerful enough to be able to learn different types of dynamics. So it may be a little bit incapable. At the same time, if you have too many neurons, this will be running the risk of overfitting your data. So I really want you to think of the neurons in the hidden layer as the order of the model. And remember, we talked about this in regression, that if, for example, you go to lower order models, like linear models, for instance, sometimes they are not sophisticated enough to be able to learn the dynamics of the underlying problem. On the other hand, if you go to very, very high order models, sometimes what they do is they start overfitting your data. So you want to basically stay clear of both these extremes. Typically, what people do is either pruning or growing. In pruning, you basically start with a network with a very large number of neurons in the hidden layer, and then you start removing the neurons one by one and observe how the behavior of the system, for example, how the error would change over time. When you start getting to a place that by removing a neuron, error suddenly goes up, you realize that that's the optimum number of neurons for this particular problem. Growing would be the opposite approach. You start with a small set of neurons, for example, one or two. You start adding to those, and then you observe um, the behavior of the system, for example, in terms of errors function. As you start increasing neurons, the error will go down. You increase it further, error will go down further. You add one more neuron, error becomes even less. You reach a stage, however, that when you increase one more neuron, the error doesn't change that much. So that tells you that this additional neuron is not adding much to the problem, to the neural network capability. So the previous set of neurons in the hidden layer, that would be the optimum size. So this is where we're going to stop today. This is a list of references for those of you who are interested in knowing more about neural networks. These are good reads. One of the kind of the golden textbooks for neural networks is this book by Simon Haykin. This is a little bit old, was written in '98, but it still lays the entire foundation for neural networks, for multilayer perceptron, for radial basis functions, and it goes through the details of backpropagation algorithms. So if you're interested in doing some work with neural networks, I would recommend that you read this book, or at least a few chapters of it that are more relevant to RBF and MLP, and then consult the other references. So at this point, what I'll do is I will